Hello learners, welcome to yet another lecture on dynamic programming, and in this lecture we will discuss about Bellman-Ford algorithm. So what is the Bellman-Ford algorithm? Given a directed weighted graph G with n vertices and m edges, the Bellman-Ford algorithm is used to find the shortest paths from a given vertex S, say source, to all the other vertices in this graph, right? So this is similar to Dijkstra, right? Dijkstra algorithm is also used to find single source shortest paths. Bellman-Ford algorithm is also used to find the single source shortest paths, right? So there is a single source S. So then what is the difference between Bellman-Ford algorithm and Dijkstra's algorithm? Dijkstra's algorithm, first of all, is based on greedy approach, right? While this Bellman-Ford algorithm, it is based on dynamic programming approach. Okay, so both of them are used to find the single source shortest path, but Dijkstra's algorithm cannot work in the graph in which edges have negative weights, right? Edges can also have negative weights, but so far we have only considered those graphs in which the weights of the edges was positive. Okay, so if there happens to be a graph G which has some edges having negative weights, Dijkstra's algorithm will not give you the correct solution for that, right? In that situation, we can use the Bellman-Ford algorithm. So let us talk more about negative weight edges. So the graphs can have, as I told you, can have edges which are labeled with negative weights, right? So where these negative weights are found in the real world, let us consider some examples. If weights on the edges represent money, then think of the scenario where you have a taxi driver, and when the taxi driver picks a person from the airport and drops him or her to the city, then he will earn some money, right? Because that person will give him some fare, right? So it means you are earning money. So this is a positive edge, right? Positive edge from the airport to the city, right? Now, from the city, so from some point in the city, the taxi driver has to go to some other point, right? And it may happen that at this point he does not get any passenger, right? So he will travel empty to this point. So in this path from this point to this point, he earn money? No, he will certainly not earn money. Will he lose money? Yes, he will lose money. Why? Because it will cost him to travel from this point to this point, right? Because it will if he wants to go from this point to this point, then he has to burn some fuel, right? So it means this is a negative edge, right? So it means some segments earn money and some segments lose money. So this is one example where the edges can also have negative weights. Okay, so let us consider one more scenario. Chemistry. In chemistry, suppose nodes represent the compounds, okay, and edges represent the reactions, right? So compound A, compound B, compound C, compound D, okay. So these edges represent the reactions, right? So here the weights represent the energy absorbed or released by the reaction. So when there is a chemical reaction between A and B, then if we say that the energy is released, then we say that it is having a positive weight, right? And when there is a chemical reaction between A and C, assume that energy is absorbed, then in that case it will have a negative weight. So this is about the concept of negative weight edges in graphs, right? From the concept of negative weight edges, another concept which is called negative cycle, it comes into existence. So what is a negative cycle? The negative cycle is created by negative weights. Negative weights may create a negative cycle, but they do not always create a negative cycle. Okay, so what is a negative cycle? It is a loop or a cycle which is having total weight negative. Okay, and if you repeatedly traverse a negative cycle, then your total cost of that cycle will keep on decreasing and decreasing and decreasing without any bound. Okay, so if this is the scenario and you want to solve the problem of shortest paths, then you may not find a correct solution using the approach such as Dijkstra's algorithm, right? So let us look at this graph. This is the graph which is having four nodes A, B, C and D, and there are some edges, right? So all the edges except this are having positive weights. This is having a negative weight. So this graph, it means is having a negative weight edge. Okay, edge with a negative weight. And now let us analyze whether this graph is having negative cycles also. So here is the cycle B to C, C to D and D to B. Okay, and the total weight here is 5 plus 3 minus 10, which is minus 2. Okay, so it means this is a negative cycle. This is a cycle with total negative weight. Okay, and if you repeatedly traverse this cycle, right, again on the first traversal the weight is minus 2 and again you traverse it, minus 2 plus 5 plus 3 minus 10, now it will be minus 4, again you traverse it, it will be minus 6 and so on. So it will keep on decreasing if you repeatedly traverse this cycle, and every time it means you are getting a lower cost. So will you be able to find the optimal solution to the shortest paths problem using this kind of a graph which is having negative cycles and using the algorithm such as Dijkstra? The answer is no. Okay, so then what is the solution? The solution is to use a Bellman-Ford algorithm, which is not a greedy approach, which is based on the dynamic programming approach. Okay, so when there are no cycles of negative weight, then it gives you the shortest paths between the source and destination. Destination is this here it is written that there is only one destination, but this algorithm actually gives you the shortest paths between the source and all other vertices. Okay, this is slower than Dijkstra, but it is more versatile, right? Because it is capable to handle some of the negative weight edges. So if your graph has negative weights, then it is able to give you the correct solution to the single source shortest path problem. And if there is a negative cycle in the graph, then it is able to detect the presence of the negative cycle and it reports the existence of such a cycle, right? So the problem which this algorithm addresses is that of the shortest paths. Okay, so what are shortest paths? Shortest paths are simple paths. if you are able to recall a simple path, the definition of a simple path is a path which has no repeating vertices. The vertices do not repeat. Okay, so it means the edges also do not repeat. Okay, so there is a source and there are some intermediate vertices and there is a destination. Okay, so if this path is having n vertices, total n vertices, right? Then how many edges will be there in this path? N minus 1 edges will be there. Okay, so as I told you, you never visit the same vertex twice. There are no repeating vertices. So the length of the shortest path with n vertices is a simple path with n minus 1 edges, right? So there are n vertices, then there will be n minus 1 edges, right? So that this thing works as the basis for solving the shortest path problem using the Bellman-Ford algorithm. So let us look at the intuition behind it. The intuition is the principle of relaxation. So the Bellman-Ford algorithm works by overestimating the length of the path starting from the source vertex to all other vertices. So at the very first iteration, it overestimates the length of the path. So what is the overestimate? Overestimate is that the length of the path from S to every other vertex is infinity. So this is the maximum length which can be possible between a source vertex and other vertex vi. Okay, so this serves as our base case, and if we think of it in through the lens of dynamic programming, then it means these are your basic subproblems, and using these basic subproblems you will construct the solution in the bottom-up fashion for other subproblems which are dependent on these basic subproblems, and ultimately we will be able to find the solution for the complete overall problem, right? Okay, so using these basic subproblems, then it iteratively relaxes those estimates. Okay, so if initial estimate is infinity, then if it is finding a better path, if it is finding a new path which is shorter than this previously overestimated path, then it will update it. Okay, so if you are finding a better path, suppose it is 10, then it will be changed, and this is done iteratively. Okay, so how is this algorithm working? So initially the distance s, it means suppose this is a table, this is an array which will store the distances from the source vertex to all the other vertices. Suppose there are 1, 2, 3 and n minus 1 vertices. Okay, because as we are not considering it here, right? So total there are n vertices, and except the source vertex, all other vertices are numbered from 1 to n minus 1. So this is one more basic subproblem or the base case. So where we initialize the distance to the source node equal to 0, because we are at the source node. So it will be initialized to 0, and also the distance to all other vertices from the source node, as I told you before, it will be infinity. So this is the very first before starting any iterations, this is the initialization. So these are the base subproblems which we have solved, right? Now we will update all edges n minus 1 times. So there will be a loop which will be running n minus 1 times. Why n minus 1 times? Remember that in one of the previous slides, I told you that the shortest path, if there are n vertices, then the shortest path will contain n minus 1 edges. Why? Because there, if it is a shortest path, then no vertices will be repeating, right? So there will be no loop. Suppose this is a loop. Okay, so here what are you doing? So this is v1. Suppose this is some vi and this is vn, right? So here from vi we are going to some other vertices and again we are coming back to vi. So we are visiting vi twice, right? So there will be some positive weight of this loop, right? So if there is some positive weight which we are adding here, and here also we are having some weight. Suppose its weight is 7, its weight is 5, and its weight is 2. Okay, so which is the shortest path? The path which is going through this loop, or the path which is not going through this loop? Okay, so we can see that if we traverse this loop, the total path length will be 5 plus 7 plus 2, which is 14, right? And if we do not visit this loop, we directly go from v1 to vi to vn, then this path length is only 7, right? So there must be no repeating edges if this is a shortest path, right? So if there are n vertices, there must be n minus 1 edges in the shortest path, right? So therefore we are running a loop in this Bellman-Ford algorithm n minus 1 times, right? Because there are n vertices in your graph, so the shortest path at the max can contain n minus 1 edges. It cannot contain more than n minus 1 edges, right? So if it has more than n minus 1 edges, it means some of the vertices are repeating, and if the vertices are repeating, then it is not a shortest path, right? Okay, so this thing is clear. Now how to calculate the shortest path? This is the recursive formulation through which we calculate the shortest path. So distance I, suppose this array is your distance, okay, and distance I, here I stands for the iteration, okay. So how many iterations are there? There are n minus 1 iterations, right? So in the zeroth iteration, actually we are not performing the zeroth iteration. Zero means you are not considering any edge in between. You are yeah, so this is the initialization. Okay, so there is also a zeroth iteration when I is 0. I is 0 means you are considering only the direct paths. Okay, so there is no edge, there is no vertex in between. Okay, so if it is distance 0, u can be any vertex, is equal to minimum of distance I minus 1. So here if it is 0, so we will look at this matrix which we initialized before this loop. Okay, so it will update the distance if we are able to find a better distance. Okay, so it will look at the previous distance. Suppose this is my I here is minus 1, suppose. Okay, so I minus 1, k is another vertex, comma distance I minus 1 j. Okay, so I think I made a mistake here. It should not be u, it should be k, right? So we are updating the distance of a vertex k. Okay, so it is minimum of the previous distance or the new distance. So what is the new distance? The new distance is the previous distance of what, so here we are considering an h. So what is that h? H is j comma k. Okay, so it is weight of that h, j comma k. Okay, and we will consider it for all the edges. Okay, so we will update for all the edges. So what we are doing here actually, so suppose k is so this is your graph a, b, c, and there are some edges and there are some weights 10, 5, 4. Okay, so it will be a, b, c only, right? And suppose the source vertex is a, we also have b and c, and they will be infinity. Okay, so we are updating it for all the edges. Okay, so we are doing it for all the edges, this loop. jk means all the edges. So what are the different edges here? There are 3 edges, ac, ba and bc. Okay, so first of all we will look at suppose this ac. So here k is a, let me write it here only, a. So we are updating the distance of a. It will be minimum of distance of a and distance of okay, it can if we are talking about this vertex, then k must be c, right? Here we are updating the distance of a destination vertex. So distance of previous distance of c and the distance, the previous distance of a comma the weight which is connecting this HA to C. Okay, so this is the inductive formulation. And now what is the minimum? The previous distance of C was infinity. Now we are considering this direct edge A to C. Okay, so the distance to A which we have calculated in the previous initialization is 0 plus the weight of this edge A to C is 10, right? So we are updating it because we are getting a minimum value, right? Okay, similarly let us consider the next edge. This is B to A, so that destination is A. So here A and here this is B to A, so this will be the recursive formulation. Okay, right. So the distance, the previous distance of A is 0 and the distance of B is infinity and the weight of the edge from B to A is 5. So already we have minimum which is 0, so we will not update it. Similarly, let us consider this edge. This is B to C. So now the destination is C. C. This is right. From B to C. Okay. So the previous distance of C, yeah. So it is 10, right? And the distance of B, the previous distance of B is infinity and B to C the distance is 4. So the minimum will be 10. So we will keep it equal to 10. Okay. So this was the 0th iteration, right? 0th iteration means when there was direct connections between the source and the destination. Okay. So now we have solved the subproblems in which there was a direct edge. What was the shortest paths when there was a direct edge, right? You can see here also that if you want to go from A to C without using any intermediate vertex, then the shortest path is 10. And if you want to go from A to B, is there any direct connection? No, there is no direct connection. Therefore, it is infinity, right? So this iteration solves the subproblems in which you do not have any intermediate vertex. Now in the next iteration, I will be 1. I will be 1 means you will now solve this problem using one intermediate vertex. Okay, so it means you will look at the subproblem which was solved in the previous iteration when I was 0. So we will look at this. Okay, and again we will solve it for all the edges in your graph. So there are 3 edges. Okay, so the first is A to C. So here we will update the distance of C, and now we will look at distance. We are calculating distance in iteration 1. So we will look at the previous this array. So distance 0. Okay. So A to C. So the source is C. Okay, so the previous distance of C is 10 and distance of A is 0 and the weight from A to C is 10. So it will not change. Okay, and if you consider B to A, your source is A, sorry, destination is A. So we are calculating the distance to A from B to A. Okay, so the distance of A is 0, the distance of B is infinity, and B to A is 5. So again, this will not change. It is already minimum, it is already 0, so it will stay 0. Then let us consider this one, the last one. Here, B to C. Okay, so here again the destination is C, and C here, B to C. Okay. Distance of C is 10, distance of B is infinity, B to C is 4, so we will not change it, it will also be 10, right? So this is what happens at the iteration number 1. Okay, so these iterations will be till n minus 1. So n is 3 here, so n minus 1 means 2. So now we are at the last iteration. Okay, so now we are calculating distance 2 and we will look at distance 1. Okay, so we are solving the previous subproblems, and from those previous subproblems we are solving the newer subproblems. Okay, and now this is the final iteration which will give us the final shortest paths, right? Okay, so I think nothing will change in this also, right? So A to C, destination is C and source is A. Already we have calculated. This was a very simple example. So A to C, right? Okay. So the distance of C is 10. The weight or distance of A is 0 in the previous iteration, and the weight A to C is 10. Okay, so both are same, we will not change. Okay, similarly B to A, A's distance is already 0, we cannot have less than this, so this will also not change. And B to C, the minimum distance we have already calculated is 10. If we add the distance of B, the B's distance is infinity. Infinity plus 4 will be infinity. So this is better. So again this will not change. So this is the final shortest path. From A to A the distance is 0. From A to C the distance is 10. And from A to B, if you look at this graph, there is no path, right? Therefore it is infinity. Okay, so this is how we solve this problem of shortest paths using Bellman-Ford algorithm, and here we use the concept of dynamic programming, iteratively solving the sub problems. Okay, and here at the last iteration it was i's value was 2. It means now we were considering two intermediate edges, intermediate vertices, sorry. Okay, so because there are three vertices, so at most your shortest path can contain n minus 1 edges, right? Okay, so let us run the Bellman-Ford algorithm on this graph. This graph is having 6 nodes and it is having 8 edges. Some of the edges are having negative weights, like this edge from D to A, and this edge from C to B, and this edge from D to C. Okay, but this graph does not contain any negative cycle. Okay, so we will create this kind of a matrix for this graph, right? So these are the different vertices which we have listed here, and these are the number of iterations for which this graph will run. Okay, and for explaining the Bellman-Ford algorithm, let us take the help of this animation. Okay, so this is the same graph which I showed you in the presentation. So I have created here, this is www-m9.ma.tu.de. so you can create any graph here and run the Bellman-Ford algorithm. So I have created the same graph, except that here I have nodes A to F, A, B, C, D, E, F, and in that graph I have nodes S, then A, B, C, D, E. Okay, so it means A is S and B is A and so on. Okay, so everything else is same. Okay, so now let us run this algorithm. Okay, so it is saying let us first choose the starting node. So this is the starting node, this is now our S, so this is now symmetric to the presentation. Okay, so let's run it. Okay, so first of all it will do the initialization. Okay, so initialization means S is initialized to 0 and all other nodes distances are initialized to infinity. Okay, so we can do here that this is 0 and all other distances are infinity. Okay, so this is step number 0 here, right? Okay, so let's go to the next step, and this there will be total 5 phases as we have listed here, 1 2 3 4 5, because there are 6 vertices. So this algorithm will run n minus 1, that is 5 times. Okay, so now we will calculate the shortest paths using at most 0 edges. Okay, so it means we will calculate the direct paths. Okay, so first it is checking this edge, so it will check all the edges one by one. Okay, so it is randomly picking the edges. So here this is the source and this is the destination, and it is saying that the distance is 2, so infinity plus 2 is infinity, so it means the distance cannot be updated. Okay, so let's move next. This is picking this node, so this is S node, and this is connected by weight 10 to another node. Okay, so 0 plus 10, the new distance is 10, which is better than this infinity, so we will update this distance. So if we see here, this is from S to A, right? So this will be updated, this will become 10, right? Again let us run it. Now it is considering this edge, so again here it is 0 and the weight of this edge is 8. 0 plus 8 is 8, which is better than infinity, so this will also be updated. So it is S to E. Okay, so this will be updated, and then it will consider other edges. So this is the edge which is considered next. This is infinity plus 2, which is infinity. So weight cannot be updated. Similarly, this edge, it will not be updated. This edge will not be updated. This, okay, so I think, yeah. So now we are considering this edge. So the weight here is 8, right? The weight here is 8, and this is the source and this is the destination. 8 plus 1 is 9. New distance is 9, which is better than infinity. So it will be updated. Okay. So if we look here, this is this one, E to D. Okay. This E's distance is 8 and E to D, the distance is 1. It will be 9, right? So in this first iteration, so far we have updated 3 edges which are indicated by a green here. And next, the next edge which we are considering is from this 9 to 10. Okay, so this is 9 minus 4. The cost of this edge is minus 4, so it will be 5, and the cost of target node is 10. Okay, so 5 is better than 10, so it will be updated. Okay, so from D to A, right? So this is from D to A. The A's cost, previous cost is 10. Now it will be 9 minus 4, it will be 5, right? Okay, so let's move ahead. Okay, so now we are considering this. This is infinity plus 1 is infinity. So the target node's cost is 5, so it will not be updated, right? So let's move ahead. So we have now visited all the edges one by one and updated the edges. Okay, so the values which we are getting are 0 at the source node, and then we are getting A's distance 5, then this is I think E, which is 8, and 9, this is D. Okay, so all other are infinity. So this is also infinity, this is also B and C. I think there is a 5 also. Yeah, this is A. Okay, so all other are infinity. This and this, they are infinity. So this is the first phase. We have completed the first iteration. Okay, so now we have calculated the shortest paths using an H. Okay, then we will using one edge, right? So there was no intermediate vertex, right? Now we'll in the second iteration we will update the distances using at most, this was one edge, means no vertex in between. Now these are two edges, means there in between there is one vertex. Okay, okay. So in the same manner we will look at the distances. So first we are considering this 5, the distance of source, and from source to destination the distance is 2. 5 plus 2 is 7, which is better than infinity. So we will update it. Okay, so 5, and this is node A. From node A we are going with distance 2 to another node. Okay, so this means we are updating the distance of C, right? It will be 7. Okay, so it will be updated. Let's run it again. Now we are considering this 0 plus 10 is 10, and the destination is 5, so it will not be updated. Let's run again. 0 and the distance is 8. Already there is 8. It will not be updated. Next, this vertex 7, and distance here is minus 2. So the new distance will be 5. So it means this 7 is, we are talking about C. So C is 7, and from there with minus 2 we are going to B. So B's distance will be changed. B's distance will be 5. Okay. Let's run again. Now from this 9 we are going to 7. But the distance will be 8. Already we have a better distance, so it will not be updated. Let's move ahead. 8 to 9 we are going, and 8 plus 1 is 9, so it will not be updated. Next we are considering this 9 minus 4 is 5. Already we have 5 here, so it will not be updated. And then I think this is the last edge which we are considering. 5 plus 1 is 6. Already we have a better distance here, it will not be updated. Okay, so we have completed the second iteration also. So other edges, other distances will simply be copied. Okay, now let us move to this iteration. Now we are considering at most 3 edges. Okay, so it means in between there are lying 2 vertices. So for this we will take the help of these previous subproblems, right? Okay, so we will again update the distances of all the edges. Okay. First we are considering this 5 plus 2 is 7. Already there is 7, we will not update it. Then this 0 plus 10, 5. Already there is 5, we will not update it. Then 0 plus 8 is 8. Again, no updation. 7 minus 2 is 5, no updation. Then 9 minus 1, 8, no updation. Then 8 plus 1, 9, no updation. Then 9 minus 4, 5, no updation. And this is the last edge, 5 plus 1, 6, no updation. Okay. So here in this phase we did not update any edges. Okay, so now we are ready to move to the next phase. Let me copy all the solutions from the previous iteration. Okay, now we are here. Here we are using 4 edges. Okay, so again we will consider one by one. So I will just go through. I think no updation will be done here, right? So we have checked all the edges and there is no updation. Okay, so 0, 5, 5, 7, 9, 8. Okay, now we are at the last iteration. Here we are considering 5 edges in between. And let me go through this execution. Okay, so here also in this 5th iteration there was there were no updations. Okay, so right, and this is the final shortest paths, right? After running this algorithm for by considering all the 5 edges in between. Okay, so now how to find the negative cycles. Okay, so we have considered the shortest paths, and the shortest path, there were 6 edges, so the shortest path can contain at most 5 edges. Okay, so now how to check for negative cycles? Let us again check again run this algorithm, and if for the 6th time you still get a shorter path, it means your algorithm contains a negative cycle. Why? Because if you repeatedly iterate over the negative cycle, you will get the cost decreased every time. Okay, it will decrease till infinity. Okay, there will be no bound on decreasing. Okay, so if this cost still decreases, by running the algorithm for 6 times, it means your Bellman-Ford, your graph contains a negative cycle. Okay. So here we are running again, and first we are checking this edge. The cost is not being updated. Now again, cost is no updation. So we already know that there will be no updations if we run it for the 6th time. Okay. Why? Because we already saw that updations was only till this iteration. Okay. There were no updations in third iteration, no updations in fourth iteration, no updations in fifth iteration. Okay. So obviously there will be no iteration in this particular graph in sixth iteration also. Okay. And these are the minimum cost weights for reaching from S to A, S to B, S to C, S to D, and S to E. Right. Okay, so now we will look at the implementation. Implementation is very similar to the explanation. So initially we set all the nodes distances except the starting node to infinity. We set the distance of the starting node to 0, and we run this algorithm. If there are n vertices, we run this n minus 1 times, and in each iteration we will consider all the edges, and we will update the edges depending upon whether the previous distance to the destination is better or the new distance from the source j plus the edge connecting this source to k is this weight, using the distance of j plus the weight of this edge. Are we getting a better distance as compared to the distance which we already have there? Okay, so this loop is run n minus 1 times. Okay, and when we finish this loop, we get the minimum cost weights for reaching from source to all other nodes. Okay, and at the end we can run it one more time for all edges. We can again check whether there is a decrease in the cost of any particular vertex. If there is still a decrease in the cost, it means your graph contains a negative weight cycle. Okay, so in this way this algorithm also reports whether your graph contains a negative cycle or not. And now let us move to complexity analysis. So the outer for loop, it is running n minus 1 times. So it means its complexity is order of n times. And in each iteration, we traverse through all the edges and calculate the shortest distances. Okay, so if you have to identify all the edges using the adjacency matrix, then it will require time order of n square. And if you use adjacency list, in the adjacency list, order of m number of operations will be required, because there are m edges. We assume that there are n vertices and m edges. So the time, the structure of adjacency list, if you can recall, is such that if you have to traverse through all the edges, then the time it takes in the adjacency list is equal to the number of edges, right? So overall time complexity depends on whether you are using adjacency matrix or adjacency list. Okay, so if you are using adjacency matrix, then it will be order of n cube, because outer loop is running n times, and inside the loop you are scanning order of n square number of edges. So it is total n cube. And if it is adjacency list, it is order of m into n, right? And the space complexity, let's also talk about it, because we are creating an array, right? And what is the size of that array? The size of the array, we store all the vertices there, right? So if there are n vertices, the size of the array will be n. So this is the space complexity. Okay, so this is all about the Bellman-Ford algorithm using the dynamic programming approach. Thank you.